the use of pH to indicate the strength of an acid or a base is limited as its value changes with the change in the concentration. As a result, chemists looked for a better alternative and found the dissociation constant to be a better tool than the pH scale to express the concentration of weak acids and bases. Consider the dissociation of weak acid HA in water to derive the expression for its dissociation constant. As we know, weak acids dissociate to a very limited extent in water. Equilibrium between the dissociated ions and undissociated molecules is established soon. This equilibrium can be expressed as HA aqueous plus H2O liquid in equilibrium with H3O plus aqueous and A minus aqueous. The equilibrium constant for this reaction can be written as Kc is equal to the product of concentration of H3O plus and A minus ions divided by the product of concentration of HA and H2O. As the concentration of water does not change, it can be taken as constant. Hence, it may be written as Kc into H2O is equal to the product of concentration of H3O plus and A minus ions divided by the concentration of HA. Since Kc and concentration of water both are constants, their product is also constant, and it can be taken as Ka, that is, Ka is dissociation constant of weak acid. As the dissociation constant is the equilibrium constant, it is affected only by a change in temperature and not by a change in concentration. Hence, the value of the dissociation constant provides the exact measure of the extent to which an acid is dissociated. In other words, the strength of the acid. The stronger the weak acid, the greater is the extent of dissociation. The greater are the concentration of H3O plus and A minus ions, and the larger is the value of Ka. The extent of the ionization of weak acids is usually expressed in terms of degree of ionization, which is denoted by alpha. Let us take the same generic example of the dissociation of weak acid, HA, in water to derive the expression for the degree of dissociation of weak acids in water. Let C moles per liter be the initial concentration of weak acid HA, and let alpha be its degree of dissociation. At equilibrium, the number of moles of the reactants will be C into 1 minus alpha, and that of the products at will be C alpha and C alpha respectively. The dissociation constant Ka for this dissociation equilibrium can be written as Ka is equal to the product of concentration of H3O plus and A minus ions divided by concentration of HA. Substituting the equilibrium concentrations in this equation, we get C alpha multiplied by C alpha divided by C multiplied by 1 minus alpha. Thus, Ka becomes equal to C alpha squared divided by 1 minus alpha. This expression helps us in calculating the degree of dissociation of weak acids when the dissociation constant is known. The values of Ka range from 0.66 to as low as 1 multiplied by 10 raised to the power minus 10 and even smaller. Hence, to accommodate such a wide range of values, the logarithmic scale is used. It is expressed as pKa equals negative log of Ka. The stronger the weak acid, the higher the value of Ka, and the lower is the value of pKa. For example, among the halogenated fatty acids, fluoroacetic acid with a higher value of Ka and lower value of pKa is the strongest. The dissociation constant Ka helps us in calculating the pH, equilibrium concentration, and degree of dissociation of a given weak acid. This problem will help you understand the steps to calculate the degree of ionization, equilibrium concentrations, and pH of a solution when the initial concentration and dissociation constant of the acid are known. The ionization constant of hydrocyanic acid is 4.9 multiplied by 10 raised to the power minus 10. Calculate the degree of dissociation, the concentration of all the species, and the pH of a decinormal solution of hydrocyanic acid. The first step in solving this problem involves writing the equation for the ionization of a weak acid in water. The equation for the ionization of hydrocyanic acid in water is HCN aqueous plus H2O liquid in equilibrium with Cn minus aqueous plus H3O plus aqueous. In the second step, set up the ICE chart. The initial concentration of hydrocyanic acid is given as 0.1 m. The initial concentration of the products is 0. Since the reaction is yet to happen, the change in concentration on proceeding to equilibrium in terms of alpha is minus 0.1 alpha for hydrocyanic acid and plus 0.1 alpha and 0.1 alpha each for Cn minus and H3O plus ions. The equilibrium concentration of hydrocyanic acid is 0.1 multiplied by 1 minus alpha and 0.1 alpha each for cyanide and hydronium ions. In the third step, substitute the equilibrium concentrations into the equilibrium constant expression for the reaction and solve for alpha. The expression for the dissociation constant of hydrocyanic acid can be written as Ka equals product of concentrations of cyanide and hydronium ions divided by concentration of hydrocyanic acid. On substituting the equilibrium concentrations into this equation, we get 0.1 alpha multiplied by 0.1 alpha divided by 0.1 multiplied by 1 minus alpha. As hydrocyanic acid is a weak acid, it undergoes dissociation to a very little extent, and hence the value of alpha is very small. Thus, 1 minus alpha can be taken as 1. Thus, Ka becomes equal to 0.1 alpha square. As the value of Ka for hydrocyanic acid is given as 4.9 multiplied by 10 raised to the power minus 10, we can write 4.9 multiplied by 10 raised to the power minus 10 is equal to 0.1 alpha square. Now, this can be written as alpha square is equal to 4.9 multiplied by 10 raised to the power minus 10 divided by 0.1. This becomes equal to 49 multiplied by 10 raised to the power minus 10. Hence, alpha is equal to square root of 49 multiplied by 10 raised to the power minus 10. This is equal to 7 multiplied by 10 raised to the power minus 5. Thus, the degree of dissociation of decimolar hydrocyanic acid is equal to 7 multiplied by 10 raised to the power minus 5. In the fourth step, calculate the equilibrium concentrations of the species in the reaction. As alpha is known, the equilibrium concentrations can be easily calculated. Thus, the equilibrium concentration of cyanide ion, which is equal to the equilibrium concentration of hydronium ion, is equal to 0.1 alpha, can be written as 0.1 multiplied by 7 multiplied by 10 raised to the power minus 5. This is equal to 7 multiplied by 10 raised to the power minus 6. The equilibrium concentration of hydrocyanic acid is 0.1 multiplied by 1 minus alpha, can be written as 0.1 multiplied by 1 minus 7 multiplied by 10 raised to the power minus 5. This is equal to 3 multiplied by 10 raised to the power minus 6. Calculate the pH of the solution in the fifth step. The pH of the solution can be calculated using the relation pH is equal to negative log of H plus ion concentration. Substituting the value of H3O plus ion in the equation for pH, you get pH is equal to negative log of 7 multiplied by 10 raised to the power minus 6. This is equal to 6 minus log 7. Log 7 is 0.8451. Hence, the pH of the solution is equal to 6 minus 0.8451. This is equal to 5.1549. Thus, the pH of a decinormal solution of hydrocyanic acid is equal to 5.1549. The ionization constant of weak bases can also be expressed in a manner similar to that for weak acids. Consider the ionization of a weak base, BOH, in water. The equilibrium for this dissociation can be expressed as BOH aqueous in equilibrium with B plus aqueous and OH minus aqueous. The equilibrium constant for the ionization of a base is called base ionization constant and is represented by Kb. The Kb for this equilibrium can be expressed as Kb is equal to the product of concentration of B plus and OH minus ions divided by concentration of BOH. The degree of ionization for a weak base can also be derived in the same way as weak acids. Let C moles per liter be the initial concentration of weak base BOH, and let alpha be its degree of dissociation. At equilibrium, the number of moles of the reactants will be 1 minus alpha and of the products C alpha each. The dissociation constant Kb for this dissociation equilibrium can be written as Kb is equal to the product of concentration of OH minus and B plus ions divided by concentration of BOH. Substituting the equilibrium concentrations in this equation, we get C alpha multiplied by C alpha divided by C multiplied by 1 minus alpha. Thus, Kb is equal to C alpha square divided by 1 minus alpha. Analogous to Ka, Kb also helps us in finding the pH, equilibrium concentration and degree of dissociation of weak bases. On extending the logarithmic scale to Kb, you can write pKb is equal to negative log Kb. The stronger the weak base, the higher the value of Kb. and the lower is the value of pKb. For example, among the alkyl amines, dimethylamine with a higher value of Kb and a lower value of pKb is the strongest base.